All right, so in the last couple videos, we were paying attention to how we could predict the molecular geometry of a compound based on its Lewis structure. What we're going to do now is we're going to kind of point out one of the big limitations of that particular VSEPR theory that we talked about. The problem with VSEPR theory is that while it allows us to predict things like bond angles pretty well, what it doesn't do is allow us to predict bond lengths. In fact, it doesn't even allow us to predict why there's a difference between a double bond and a triple bond and a single bond. In order for us to start to understand those types of phenomena, we need to look at another model for chemical bonding. And this is what we call a quantum mechanical model. Now, I said model, but I meant models. Okay. In quantum mechanical models, what we're doing is we're actually looking at the wave functions for the orbitals that the electrons are occupying. And we're using that to draw some conclusions about things like bond length and bond strength. Now, what we're not going to do is to get into this, very quantitatively and mathematically. Instead, what we're going to be doing is just kind of looking at the shapes of orbitals and seeing how that's going to influence the nature of a bond. Okay, now there are two quantum mechanical models that we're interested in. The first one we're going to look at is called valence bond theory. Okay, so valence bond theory basically has us looking at a bond not as simply the sharing of electrons, but rather due to the overlap of valence orbitals. Okay, so for example, if we're looking at a molecule like hydrogen, okay, we say that the hydrogen atoms are going to be attracted to one another via this mutual attraction for the electrons that they're sharing, which is still important. But we also have to remember that the electrons that are being shared are already being held in a particular region around the atom that it started off with. So we have to be able to say then that if we have one hydrogen atom, that its single electron is going to exist in its 1s orbital. Okay, and the same thing can be said for the other hydrogen atom. Okay, so the dots at the end are at the center there represent the nuclei, and then the circles around them represent the 1s orbitals. And what valence bond theory tells us is that the overlap of these two orbitals is what leads to the bond forming. Or at least that the bond forming requires the overlap of these two orbitals. Okay, what's nice about this is that this actually explains a good deal about why some bonds are longer than others. For example, if you were to look at the halogen acids, so HF, HCl, HBr, and HI. Okay, it turns out that the bond lengths for these four compounds are not the same. It turns out that HF is a fairly short bond length, with HCl being longer and HBr being longer than that, and HI being even longer than that. But how do we justify this? Well, we know that as we go down the periodic table, with each row that we go down, we're adding an entire shell of an electron, or shell of electrons. So our principal quantum number is increasing by 1 every time we go down 1 row. So whereas in each one of these molecules we have the 1s orbital of the hydrogen atom involved in the bond. Okay, for fluorine, it's going to be a 2p orbital. Chlorine is going to be a 3p orbital. Okay, bromine is going to be 4p, and iodine is going to be 5p. Okay, and we know that as we go down the periodic table, as we add an additional shell, we're increasing the size. Okay, so for the hydrogen and the fluorine, okay, the hydrogen's going to be relatively small compared to the fluorine's probably going to be pretty close in size. Okay, and that's what we would expect the molecule to look like. Chlorine is going to be bigger than fluorine. Okay, so if we were to look at the distance between the centers of these atoms, okay, we can see the bond length is getting longer. We go down to HBr. Okay, we see the bond length gets even longer. And then for HI, the bond's even longer than that. I know these aren't perfect spheres, but you get the idea. Okay, so this explains why the atoms, or why the bond lengths are going to be different from atom to atom. Okay, and we can actually represent this mathematically, or at least in terms of bond energies. Okay, so let's say we were to look at the potential energy involved in a bond forming. Okay, and we look at that potential energy as a function of the distance between the two nuclei. So that's that distance right there. Okay, so when we're far to the right, the distance between the atoms is essentially infinite. Okay, but as we go from right to left, the atoms are getting closer and closer. Okay, so what we find is that over time, or over distance, I should say, as the atoms are, an infinite distance away from one another, which could be millimeters, if not less, there is no potential energy between them. But as they get together, get closer and closer to one another, okay, they're feeling the effect of each other, they're starting to feel more stabilized, and we see that the energy actually goes down, becomes more stable. Okay, more and more stable as the energy continues to decrease. Okay, but eventually we're going to get to the point where the atoms are just too darn close together. Okay, the nuclei are getting too close together. Okay, and we're going to start seeing the energy go right back up again. And it's going to just take off. And obviously you can't have two atoms occupying the same space, so you're not going to ever have this thing reaching R equals 0. Okay, so this takes off to infinity. So it turns out then that there's this sweet spot, okay, right here, an area of minimum energy. And whatever R is at that point, that's going to be the bond distance, or the bond length, because at that length, the two atoms are close enough to to be able to feel the effects of the other atom's electrons, but not so close as to experience any repulsive forces. So this model does a very nice job of allowing us to explain bond lengths. But what it does not do, though, is explain bond angles. Because if we're going to talk about bonds forming due to the overlap of orbitals, well, we know there's only a certain number of orbitals that are available to us. Okay, we have s orbitals, which are spherical, p, which were the dumbbell-shaped ones, the d, which were kind of like clovers, and then f, and so on. But we've already talked about a large number of molecules that can include only an s or p orbital, okay, particularly like fluorine. And what we start to realize is that only certain bond angles would be allowed if we were using a p orbital in order to have the overlap for the bond to form. Because remember, the p orbital can either be lined up with the x-axis or the y-axis or the z-axis. I'm not going to draw the z, but no matter how you slice it here, we would expect all the bond angles to be 90 degrees. And that is not what we see. I mean, how do we explain a 120 degree bond angle that we see in a trigonal planar compound? Okay, how do we explain tetrahedral even? And that's what we're going to have to look at here. And in the next video, we're going to see how it's not just one s orbital and two s orbitals and two p orbitals that are combining, but rather we can have orbitals within an atom combine, undergoing what we call hybridization. And that's going to be the subject for the next video.